Hi all, I'm JISHNU. Today I would like to present a seminar on the topic called Regularization for Deep Learning. Let us move on to the main index of this section. First we will start with regularization, then we will discuss about L2 regularization, then L1 regularization. Thirdly we will discuss about what does regularization achieve, then finally we will discuss about the dropout regularization, and lastly, I will summarize the points and I will attach to the summary slide. And I had attached my reference that I made to make this slide. Let me begin with introduction to regularization. What is regularization? Regularization is a key component in preventing overfitting. Now you would have a question about what is overfitting. Let me explain what is overfitting. Overfitting refers to the phenomenon where a neural network models the training data very well but fails when it sees new data from the same model domain. Overfitting is caused by noise in the training data that the neural network picks up during training and learns it is an underlying concept of that. Simply, it is a imbalanced data in the model. So I will give a perfect example for overfitting in the next slide. Before moving that, let me explain what is regularization. Simply, regularization refers to a set of different techniques that lower the complexity of a neural network model during the training and thus prevent all the overfitting problems. There are three very popular and efficient regularization techniques called L1, L2 and dropout, which we are going to discuss in the following slide. Now I will give an example for overfitting model. Here you can see a better model. The data are balanced correctly and there is no noise in the data in better model. But in overfitting model, you can see that the imbalanced data is present in the model. That is why it is become overfitting. So to solve this problem, we are using regularization techniques. Let us move on to the first technique, that is L2 regularization. In the L2 regularization, it is the most common type of all regularization techniques and is also commonly known as weight decay or ride regression. During the L2 regularization, the loss function of the neural network is extended by a so-called regularization term, which is called here omega. Here, regularization term omega is defined as the Euclidean norm of the weight matrices, which is the sum of overall squared weight values of a weight matrix. The regularization term is weighted by the scalar alpha divided by 2 and added to the regular loss function that is chosen for the current task. This leads to a new expression, that is L of W equal to alpha by 2 W squared plus L of W equal to alpha by 2 double summation Wij square plus L of W. And alpha is sometimes called regularization rate and is an additional hyperparameter we introduce into the neural network. Simply speaking, alpha determines how much we regularize our model. In the next step, we can compute the gradient of the new loss function and put the gradient into the update rule for the weights. Here you can see the two equations and some formulation of the update rule lead to the expression which very much looks like the update rule for the weight during regular gradient descent. This is the new equation we got. Okay, I hope you can understand this, and let us move on to the L1 regularization. In case of this L1 regularization, also it is known as lasso regression. We simply use another regularization term omega. This term is the sum of the absolute values of the weight parameters in a weight matrix. Here you can see the equation omega of W equal to W of 1 equal to double summation Ij Wij determinant. As in the previous case, we multiply the regularization term by alpha and add the entire thing to the loss function. Here you can get the equation, and the derivative of the new loss function leads to the following expression, which is sum of the gradient of the old loss function and sine of weight value times alpha. And omega of w, L of w equal to alpha sine omega plus delta omega L of w. Let us discuss about what does regularization achieve. Performing L2 regularization encourages the weight values towards zero, but not exactly zero. And the performing L1 regularization encourages the weight values to be zero. And intuitively speaking, smaller weights reduce the impact of the hidden neurons. In that case, those hidden neurons became neglectable and the overall complexity of the neural networks gets reduced. As mentioned earlier, less complex models typically avoid modeling noise in the data and therefore there is no overfitting. But you have to be careful when choosing the regularization term alpha. The goal is to strike the right balance between the low complexity of the model and the accuracy. If your alpha value is too high, your model will be simple, but you run the risk of underfitting your data. Your model won't learn enough about the training data to make the useful prediction. If your alpha value is too low, your model will be more complex and you will run the risk of overfitting your data. Your model will learn too much about the particularities of the training data and won't be able to generate the new data. Finally, we can figure out the dropout regularization. In addition to the L2 and L1 regularization, another famous and powerful regularization technique is called a dropout regularization. This procedure behind dropout regularization is quite simple. In a nutshell, dropout means that during training with some probability p, a neuron of the neural networks gets turned off during the training. Let's look at the visual example. Assume on the left side we have a feed forward neural network with no dropout. Using dropout with less, let's say a probability p equal to 0.5, that a random neuron gets turned off during training would result in a neural network on the right side. In this case, you can observe that approximately half of the neurons are not active and are not considered as a part of the neural network. And as you can observe, the neural network becomes simpler. A simpler version of the neural network results in a less complexity that can reduce overfitting. The deactivation of the neurons with a certain probability is applied at each forward propagation and weight update steps. This is all about dropout. Let us summarize the main points that we discussed in this slide. That is overfitting. Overfitting occurs in more complex neural network models. That is many layers, many neurons. Complexity of the neural network can be reduced by using L1 and L2 regularization as well as dropout. We can reduce the complexity using this L1 regularization and L2 regularization as well as dropout regularization. In L1 regularization, it forces the weight parameters to become zero value, and the L2 regularization, it forces the weight parameters towards zero, but never exactly zero. It just forces the parameter towards zero only, and the smaller weight parameters makes the neurons neglectable. It implies neural network becomes less complex and less overfitting. And during dropout regularization, some neurons get deactivated with a random probability p, and the neural network becomes less complex and less overfitting. And here is all about my topic. I think I hope you can all enjoy the seminar, and these are the reference I made for creating this seminar. And thank you for listening my seminar. If you have any doubt, feel free to ask. And thank you.